Lubricants are the lifeblood of engines, turbines, and other machinery with moving parts. They serve not only to lubricate moving parts by reducing friction, but they also act to draw waste heat away from engine components, they clean surfaces, and they protect parts from corrosion and excessive wear. Most of us are familiar with the idea of getting an oil change in our vehicles at certain mileage or time intervals. Conceptually, and in the broadest sense, we understand that as the engine is run, oil gets dirty and becomes less efficient at performing its intended role. This can be visually apparent as the color of passenger car motor oil changes from golden and honey-colored when new to dark black-brown throughout its use. The very same is true for larger engines, heavy machinery, turbines for power generation, and much more. Importantly, the volume of lubricant used in these applications can be thousands of times larger than that in a common passenger car. These machines may also require expensive formulations of lubricants to ensure proper functioning. Lastly, taking this machinery out of service can be expensive in terms of productivity loss. Of course, there is more to the degradation of lubricants than them getting dirty or changing colors. Therefore, precise quantification of the chemical parameters of a lubricant during and after its use is important to many industrial users. Much like we rely on doctors to assess the chemistry of our blood to indicate unseen health concerns, reliable and accurate analysis of the chemistry of lubricants offers insight into the remaining lifespan of the lubricant, the health of the engine, or can indicate mechanical issues that need to be addressed. The chemistry, and therefore the performance of a lubricant, changes as it is used. This is primarily the result of physical, chemical, and thermal stresses imparted on the lubricant that facilitate changes in its molecular structure, for example, oxidation, nitration, or hydration of the lubricant. Contamination due to airborne dust and particulates worn from moving parts is also common. Air filters and oil filters can minimize these complications, but they become ineffective as they are used. Also, in many cases, wear metal particulates are smaller than the pore size on lubricant filters, which means they are not removed from the lubricant as it circulates through the filter. Metal particulates can be exceptionally damaging as they act as fine abrasives and beget more erosion of moving parts within the engine or machinery. Incorporation of unburned liquid fuels or partially burned fuel, or soot, also negatively affects a lubricant's properties. In the case of unburned liquid fuels, also called fuel dilution, the viscosity of the lubricant decreases as liquid fuels such as gasoline or diesel are dissolved into the lubricant. Soot particulates can foul filters and act as an abrasive, damaging moving components. Finally, aqueous liquids such as leaking coolants or water produced during combustion can be emulsified into the lubricant, reducing its effectiveness or promoting corrosion of engine components. There are a variety of techniques, methods, and types of instrumentation used for the analysis of the chemistry of lubricants. Many of the standard practices and methods used in the industry have developed by ASTM Committee D02 and various subcommittees therein. For the purposes of this webinar, we will discuss just a few of the many methods employed, including FTIR for molecular degradation and accumulation of soot, ICP AES for the analysis of additives and wear metals in lubricants, and finally, gas chromatography, or GC, for quantifying so-called fuel dilution or incorporation of liquid fuels into a lubricant. The first method that we will have a look at is ASTM E2412, using FTIR to analyze for molecular changes to lubricants such as oxidation and nitration, moisture incorporation, as well as particulate contaminant such as soot. Fourier transform infrared spectroscopy, or FTIR, has long been used for molecular analysis of all types of samples. Absorption of infrared light at distinct wave numbers is characteristic of certain molecules and bonds therein. As such, FTIR makes for a quick and non-destructive technique for analysis of lubricants to assess changes to their molecular chemistry. Shimadzu's IR Spirit is well suited to these types of analyses. Its small form factor means that it's easily transportable and takes a minimal amount of bench space. When equipped with the Pearl Liquids Analyzer or the QATRS Attenuated Total Reflectance Prism, fast, repeatable analysis of liquids such as lubricants are made simple. As engines and machinery are run and lubricants serve their purposes, physical, thermal, and chemical stresses change their molecular composition. For example, the lubricant can be subject to oxidation, nitration, or the incorporation of moisture. There are also compounds added to lubricants that are sacrificial. That is, they are intended to break down during use to protect the lubricant and the engine. An example of this are antioxidants, compounds incorporated into lubricants that oxidize during use, which protect other compounds within the lubricant itself. As antioxidants degrade, their performance is reduced. Using the IR Spirit and Pearl Liquids Analyzer accessory, lubricant analysis is as simple as placing the sample and analyzing. Here we show two spectra generated of new lubricating oils in red and the same lubricating oil after several thousand kilometers of use in a typical vehicle, shown in black. The highlighted portions of the spectra on the left show an increase in moisture content as well as oxidation and nitration occurring during use. On the right, we see another set of spectra of a different sample showing the breakdown of antioxidants as well as nitration of the oil. Interestingly, we do not observe the same oxidation spectra at wave number 1750, presumably due to the protective nature of the sacrificial antioxidant additive. The accumulation of soot, or incomplete combustion products, can also be quantified using the IR Spirit. The occurrence of soot arises from the partial combustion of fuels, resulting in dark-colored, carbon-rich particulates in the exhaust stream that are incorporated into the lubricant in a process known as blow-by. This process is not atypical and yields the common black color of used lubricating oils. However, too much soot can foul filters and reduce a lubricant's effectiveness. Because of the dark color and strong opacity of soot particulates, FTIR is very amenable for the quantification of the amount of soot in the lubricant. Here we use the IR Spirit with the QATR attenuated total reflectance accessory for analysis. You can see a small drop of lubricant placed on the QATR prism, ensuring repeatable, uniform thickness of the sample for reproducible results. Cleanup between samples is simple. Simply use a lens paper on the stage to wipe away the lubricant sample, and you're ready for another analysis. Here are some of the results of the use of our IR Spirit with QATR accessory. Absorbance around 1850 to 2000 is indicative of the dark-colored soot particulates, so quantifying the baseline position around these wave numbers correlates to the quantity of soot in the lubricant itself. To the right, we can see the linearity generated by building a calibration curve of lubricants with spiked known soot content. Analyzing samples against this curve is relatively successful. In the three examples here, the results of quantification are close to the true values. At the low end of the concentration scale, however, there is a larger analytical uncertainty, likely due to baseline fluctuations having a pronounced effect on the analytical results. Nonetheless, this instrument configuration is used successfully here for quantification. The next methods that we'll have a look at are ASTM D4951 and D5185 using ICP AES, or OES depending on the nomenclature, to quantify the concentrations of additive and wear metals in lubricants. Inductively coupled plasma atomic emission spectroscopy, or ICP AES, is often used for fast, multi-element analysis of a range of sample types. This technique is sometimes called ICP OES for optical emission spectroscopy. Regardless of the nomenclature, ICP AES and ICP OES are effectively the same. Using ICP AES, liquid sample is aerosolized into an energetic plasma source in which the sample is completely dissociated and atomized. The plasma excites individual elements, driving electrons into an elevated state. When those electrons relax to their ground state, photons of characteristic wavelengths are emitted. The same phenomenon is commonly seen in fireworks, where oxidizing different elemental compounds yields visibly different colors, such as magnesium for white and copper for blue. ICP AES offers quick and robust analysis by simultaneously collecting data for many wavelengths and therefore for many elements. It's also notably robust as a technique because once the sample is introduced, it's simply a matter of measuring the light emitted and does not suffer from complications with ions and ion optics like ICP mass spectrometry. For these analyses, we use Shimadzu's ICP 9800 series instrument. It features a vacuum-purged optical bench to minimize gas consumption and a vertically oriented plasma torch, which minimizes carryover and accumulation of matrix material. Certain elements and compounds containing those elements are added to lubricants as they are manufactured. So-called additive elements are included for their beneficial properties, such as zinc sulfur phosphorus compounds like ZDDP for their anti-wear properties. Other metals wind up in lubricants due to wear or erosion of moving parts in an engine. Analysis for wear metals such as iron and copper can indicate mechanical problems within an engine. Additive and wear metal analyses are easily carried out using the Shimadzu ICP 9800, shown here. It was configured with a torch suitable for organic solvents, a baffled spray chamber, and it was set for radial viewing mode. Here are a few atomic emission spectra of calcium and molybdenum in lubricating oils. The prominent peak is a spectrum generated from a standard used for calibration, and the smaller peaks are spectra generated from samples themselves. Below those are representative calibration curves for calcium, molybdenum, and zinc. The linear relationship between emission intensity and concentration over the analytical range is critical for accurate quantification. Results for the analysis of wear metals using the ICP 9800 series are shown in the table here. Spike and recovery for low concentration elements are near 100% throughout. Similarly, dilution test results for higher concentration wear metals are near 100% as well. These results show that whether quantifying trace metals or diluting major metals, results can be generated accurately and easily. Now we will move on to using gas chromatography methods for lubricant analysis. Though there are many methods used in practice, the ones that we will focus on here are ASTM D3524, D3525, and D7593. Gas chromatography, or GC, is the most common analytical instrument used in laboratories analyzing lubricants, oils, and related hydrocarbons due to the volatile nature of the samples. In the most simplistic sense, the sample is injected, vaporized, and directed towards a column in which constituent compounds are separated by their boiling point and their polarity. For most lubricant applications, detection is accomplished by a flame ionization detector, which is highly sensitive for hydrocarbon compounds. Using Shimadzu's GC2030 for these analyses, analysts can take advantage of the system's ease of use and versatility to their benefit. Fuels are injected into engine cylinders and turbine combustion chambers as a fine aerosol mist to maximize its combustion efficiency. However, if some of this fuel remains unburned, it can be incorporated into the lubricant film on the cylinder walls. The purpose of so-called fuel dilution analysis is to assess how much liquid fuel, such as diesel or gasoline, is mixed into the lubricating oil. This can be important to assess mechanical problems such as timing, issues with improper fuel-air ratios, degradation of seals within an engine, or can simply serve as a proxy for remaining lubricant lifespan, as small amounts of fuel are inevitably incorporated into the lubricant during its use, and excessive concentrations can indicate the need for a lubricant change. The industry standard method for assessing the amount of liquid fuels incorporated into lubricants is by GCFID hardware to determine hydrocarbon distribution and quantify the contribution of fuels to the lighter hydrocarbon portion versus the heavier portion from lubricants. We will have a look at three common test methods, ASTM D3524 and D3525 for diesel and gasoline, respectively, in used oil, and D7593 for gasoline, diesel, and ethanol in in-service oil. For all of these test methods, we use nitrogen as a carrier gas to minimize the cost of operation. However, other carrier gases can be used in the system, including helium and hydrogen, if desired. The GC hardware configuration for ASTM D3524 and D3525 is very simple with an autosampler, injector, column, and FID detector. You can see from the table that all of the instrument hardware, including the column, is identical between the two methods. The only changes are the method parameters, meaning that both methods can be run back-to-back on the same instrument without any physical reconfiguration. The primary differences between the two methods are column temperature and ramp, and detector temperature to account for the heavier hydrocarbon distribution in diesel as opposed to gasoline. Again, we use nitrogen as a carrier gas here to minimize the cost of operation. These are the results that we generated for ASTM D3524 for quantifying diesel in lubricating oils. The chromatogram in the upper right shows the diesel portion of the hydrocarbon distribution up to C19 and the lubrication oil portion at the heavier fraction. The resolution calculation between C16 and C17 was 5.7 and assures good separation of the diesel and lubricating oil portion. The calibration curve was interpolated using a linear fit and was not forced through zero. 10 repeated analyses of 4 samples yielded the results at the lower left, with concentrations ranging from 3.74 to 10.84% and percent RSDs between 0.84 and 2.29. Similar to the results generated for diesel in lubricating oils, we did the same with gasoline as the fuel diluent. For method specification, C14 is used as the cut line between the gasoline portion and the lubricating oil portion. Resolution between C14 and C16 was 7.3, again demonstrating good separation between lighter and heavier hydrocarbon components. Here we analyzed 3 samples 10 times and generated data between 0.65% and 9.81% gasoline in lubricating oil, and percent RSDs of 0.52 to 1.08. Here is a look at the system hardware configuration that we used for testing of ASTM D7593. It's similar to that used in the previous methods described, D3524 and D3525, but there's an additional APC pressure controller in the flow path that enables backflushing of the heavy lubricant fractions to vent. This shortens the runtime to between 2 and 4 minutes because we are not waiting on the high boiling compounds to elute. By comparison, the previously discussed methods have runtimes of 15 to 20 minutes to ensure full elution of lubricant compounds. In the next slide, we will go into more detail on the backflush, including tests to demonstrate that there is no carryover of the heavier lubricant oil fractions. These are the results for gasoline analysis by ASTM D7593. We used an injection of 1% dodecane to establish the C12 elution time and therefore the cut time for the backflush. The chromatogram at the top shows the gasoline portions and the engine oil portions. An analysis of running a carbon disulfide blank after backflush shows no extraneous peaks, which indicates that the backflush completely removes high boiling lubricant portions from the system and does not lead to any carryover. The calibration curve for quantification shows great linearity with an R-squared of 0.9995, which exceeds method specifications for linearity. Finally, the results of 5 samples of gasoline and lubricating oil are shown in the table to the lower left. After 10 repeat analyses, average gasoline concentrations range from 1.14 to 4.98%, and percent RSDs from 1.03 to 1.49. Some of the results for diesel analysis by ASTM D7593 are shown here. The resolution between C16 and C18 is 5.7, and the linearity of the calibration curve is excellent, with an R-squared value of 0.9996. We analyzed 4 samples 10 times to assess the diesel concentration in the lubricating oil, as well as the percent RSD. The results are shown in the table towards the lower left, where concentration averages range between 2.97% and 10.08%, and the RSD was at 1.35% or below for all 4 samples. To assess and demonstrate the long-term stability and repeatability of the GC2030 or D7593 analyses, we analyzed 3 batches of samples over 200 injections each. Percent RSD varied between 1.90 and 2.21%, which is within the specification of the method and ensures repeatable results from first injection to last. With only minor maintenance to the hardware every 200 injections, the GC2030 demonstrates excellent stability for these analyses, ensuring that more time can be spent performing analysis rather than maintenance on the instrument. The 600 analyses demonstrated here represents 40 hours of analytical time, which aligns with a complete work week of analysis while maintaining excellent repeatability. The data presented here show the applicability of the GC2030 to ASTM D3524, D3525, and D7593. So let's wrap up and summarize what we've covered in this webinar. Lubricants are critical to the functioning of engines, turbines, and other machinery. They serve to reduce friction, transfer heat, and protect engine components from wear and corrosion. Chemical analysis of lubricants is critical to ensuring the longevity of mechanical components and can be indicative of mechanical problems within the engine. Because of the value of machinery using the lubricants in question, these analyses can play an important role in a comprehensive maintenance plan that ensures their longevity. FTIR, ICP AES, and GC are three of the most common analytical instruments used to analyze lubricants, and many common methods are designated by standard test methods from organizations such as ASTM. As we've shown through the data in this presentation, Shimadzu's IR Spirit, ICP 9820, and GC 2030 all meet and exceed method parameters for common ASTM test methods outlined here. These instruments are used to address molecular changes, elemental analysis, and quantification of fuel dilution rates in lubricating oils. We at Shimadzu are proud to have been a leading global supplier of analytical instrumentation for over 145 years. We invite you to visit us at refineyourlab.com to explore other solutions for the analysis of lubricants, fuels, petrochemicals, and more.
Thank you, Dr. Farnadel, for that presentation, and thank you to our audience for attending and sending questions. In fact, we got several questions, and we'll do our best to get to as many of them as we can. If we run out of time, we'll answer you directly via email. All right, here's the first question. Here we go, Dr. Farnadel. What sorts of challenges are being faced in the lubricant analysis industry today and in the future?
Yeah, it's a good question. There are a number of challenges associated with lubricant analysis, and I'd probably say one of the most important ones recently that's emerged has been with respect to gas chromatography and the use of helium as a carrier gas. Now, as many of you likely know, helium has become more expensive and sometimes faces supply problems, which has driven the move of gas chromatography methods and analysis towards other carrier gases like nitrogen and hydrogen. So adapting methods to be usable using those carrier gases has become important. Now, in the future, lubricants continue to evolve and their formulations evolve, so there might be new analytical targets or analytes that are necessary to analyze for to accommodate for the next generation in additive packages, such as detergents, et cetera, as well as novel feedstocks that are being used to generate lubricants themselves.
Thank you for that. Here's another one. What if there is more of a target element than is anticipated and the detector on the ICP saturates?
Yeah, it's another good question. The ICP 9800 series collects data for all wavelengths simultaneously. So an operator can reprocess data in post-run to select wavelengths that are less sensitive for analysis without having to reanalyze samples all over again. The next question on our list is actually related to molecular spectroscopy, so I'm glad Sudhir is here. Again, Sudhir is our product manager for our molecular spectroscopy product line, and the question is, the Pearl accessory looks relatively easy to use, but ATR is generally the go-to accessory for FTIR. What are some of the key advantages to using the Pearl accessory over the ATR?
Thank you, Andy, for the question. I'm excited to answer this one because it is product related. As discussed in the webinar, the Pearl accessory is a transmittance accessory. On the other hand, ATR, as you know, relies on total reflectance from a crystal. Due to this, the penetration into the sample with ATR is only about a couple microns, maybe 2 to 3 microns, whereas it is 25 to 100 microns or even more with Pearl accessory, depending upon the configuration used. Obviously, this results in much better signal from Pearl accessory as compared to ATR. Another related advantage due to the same reason is that qualitative analysis is much better performed using the Pearl than the ATR. Traditional FTIR liquid measurement cells are cumbersome to use, and path length repeatability is almost always a challenge, and cleaning between the samples is a hassle. All of these disadvantages are also overcome with Pearl accessory. Well, back to you, Andy. Another question for you. How long does it take to analyze a sample with all 22 elements presented in this webinar?
Yeah, that's a good question. Now, I stated earlier that the ICP 9800 collects data for all wavelengths simultaneously. So the good news is that it takes the same amount of time to analyze for 22 elements as it does for one. It's really a function of method parameters such as integration time itself. The good news is that if necessary, throughput for samples can be improved 40 to 60% by using an AS Express or a Niagara Rapid Introduction and Rinse accessory.
Thank you for that. Another question for you again. Here it goes. Can you describe the sample introduction components used for ICP analysis of these samples?
Yeah, sure. For these analyses, we diluted the samples in trace metal grade kerosene and used a baffled spray chamber and a torch suitable for organic analysis. Something of note is that auxiliary oxygen was not required because the axial viewing jacket in the instrument was removed. So this allows for radial-only viewing and eliminates buildup of organics in the optical path.
Awesome, thank you. One more for you. Here it goes. You used nitrogen as a carrier gas in this analysis. Can other carrier gas be used?
Yes, certainly. Other carrier gases can certainly be used, provided that they are acceptable within the parameters of any given standard test method that's being applied. We use nitrogen here again for these methods to reduce costs associated with helium consumption. Shimadzu also offers hydrogen sensors for their GCs to ensure safety when using hydrogen as a carrier gas in the event of a leak. And we've also used other carrier gases such as nitrogen. All right, that's going to do it for Q&A for now. We really appreciate your attendance and asking questions. If there is a question that was asked that we didn't get to, we'll respond directly via email. So thank you again for attending this webinar. We hope you enjoyed it and have a wonderful day.